Hello, my name is Matthew Keeler, and this is my E&ME 440 final project, the acrobat control problem. For the acrobat control problem, we had a double pendulum system that we needed to figure out the optimal policy to get this pendulum to swing itself to an upward position from any state value, the hardest being when it's hanging vertically downward. This pendulum receives very sparse rewards at specific state values in the simulation that we're dealing with. And we have to use those sparse rewards to figure out what the best way to swing the pendulum to the vertical position will be. Reinforcement learning was utilized in all machine learning algorithms for this project. We have an agent, the double pendulum itself, that is acting in an environment space, the physics of the simulation. And this agent at each action gets certain values for what state it's at. In this case, the angular displacements of the two pendulum arms, and then the angular velocities of the two pendulum arms. And it also gets sparse reward data telling it whether or not it's above the reward surface. Here you'll see the actual simulation output. This is the reward height right here. And you'll see the pendulum in this configuration is above the reward height. In the bottom left, we see the data points that are actually outputted from the simulation. The new state values are the meaningful ones. The first being the absolute angular coordinate of the upper pendulum arm from the lower vertical position. The second being the relative coordinate of the lower arm in relation to the upper arm, and then the next two being the angular velocities of the upper and lower arms respectively. Here you'll see the reward that we're receiving is 0. So 0 is when we are above the reward height. When we are receiving a reward, -1 is the reward output when it is not above that height. There were a couple of questions I wanted to ask in terms of receiving visualization before I started this project. The first being, what states are purely achieved through taking random actions? So if I act randomly, do I ever get to a point where I actually hit the reward surface and that I could meaningfully do policy updates after I hit that reward surface? And you'll see in the graph on the right, this was taking random actions from the hanging vertical position. I do, when acting randomly, actually am able to hit the reward surface a couple of times within 1,000 observed states. So it can achieve swinging upward just by acting randomly, which is needed for performing policy updates later. I ran this simulation acting randomly a bunch of times, and I found that at about 126 iterations, when averaged over about 100 of these runs, is when I begin to see my first observed reward. You'll see that the observed reward tends to be when the upper arm coordinate is close to -pi or pi, and the lower arm coordinate relative to the upper arm is almost in line. It's between -pi/2 and pi/2, which follows what we were expecting for being above the line with the simulation. For my baseline model, I opted for linear Q-learning. So I had a weight matrix that was multiplied by the state values that I'm receiving from the simulation, and then by updating these weights through the above Q-learning loss function, I had different values for Q for each action. So Q1 through 3 represents the value of each state at a specific action. If I go over to my simulation here, I have my update policy code. Here I'm going through all of the epochs. I've got a learning rate that's decaying as the number of loops increases from 20% to 0. I have some initialization of the simulation. I've got my matrix multiplication here that gives me my 3 values for Q. My weights hit with the state that I'm at. And I ask myself, after doing this, what is the maximum value that I see, and where does it occur? And I'm going to take that action where that maximum occurred. Except if this if statement is triggered, instead I'll act randomly based on the explore ratio. Here I envision my next state doing a similar method as before, and I see the action that led to that next state. And then I actually do my loss function here, and then perform stochastic gradient descent, updating those weights based on the derivative of that loss function. And I'm also taking a moving average reward so I can actually see what's going on here. Now, there are a lot of parameters that affect the behavior of this. As you can see, changing parameters very much changes this surface of convergence. and it also is very stochastic already based on the randomization of the simulation in this Q-learning from just starting at the lower position. So in order to actually get meaningful information from these crazy effects on the parameters, I looped a bunch of times different gamma and alpha values, different learning rates, and different weight decay, reward decay values. And you'll see that the reward changes based on these parameters averaged 5 times after 10,000 epochs. The best reward, the one closest to 0, was achieved about a learning rate of 0.075 and 0.1 weight decay consistently. So if I actually run those parameters, you'll see this is the simulation actually under those parameters for the baseline. It begins swinging randomly until it finally hits the reward surface, and then the policy will begin to be updated. As that's running, I'll show you the average reward plots for 10,000 iterations repeated through 10 trials with these parameters. And you'll see it's a little all over the place, but eventually at 10,000, it starts to flatline at a decently high average reward value of about somewhere in between negative 0.75 and negative 0.8. And see it's more consistently now being able to swing itself back to that vertical position. This algorithm was not without its flaws. So for my updated model, I avoided making the assumption that the Q space is based on a linear combination of these state values hit with weights, and instead opted to make a neural network to determine these weights after state inputs. So I did not assume the linearity. You'll see here, I've got my, and as this is running here I've got my neural network model. For this model, I have a bunch of different networks I defined here for a different number of layers. And I have formatting here to make it acceptable in PyTorch, TensorFlow, and I basically perform the same kind of functionality as the last one, but now with a neural network in place of that weight matrix. You'll see if I compare these, well, first I did the same thing where I was changing my activation function and the number of layers I had with the same parameters as the Q-learning, and I found that the best reward that I got was a sigmoid activation with 2 nodes and 4 layers, which makes sense because the reward surface is only between -1 and 0, and sigmoid is pretty good in that range. Here you'll see me plotting the behavior of the neural network compared to the linear Q-learning, and the neural network completely outshines the linear Q-learning. It begins to hone in on a policy much earlier in number of iterations, and the policy it hones on tends to be much better than the one in Q-learning after 5,000 iterations. So the red is the neural network and the blue is the Q-learning. So some insights I had toward this problem. Q-learning is very stochastic, and the stochasticity of it makes it very difficult to refine those parameters. Those parameters change the behavior a lot, and you really have to take a lot of samples of data to figure out how that's going to change on average, and not just in the specific case that you were looking at. The linear Q was much more volatile to these changes than the neural network. The neural network did a much better job of converging to those values despite what the parameters were, but the linear Q, depending on those parameters, would never converge at a good average reward value. Mapping the average reward is also a very effective way, as you can see here, to see which policy is actually doing a better job. You can see how many observed states it begins to start converging at a better average reward value. And with that average reward, we can actually compare which one is more consistently hitting the reward surface. In the future, I would love to do this with policy gradients or some actor methods, and not just purely critic methods, because this is more relevant in the real world where the state space is much more complicated than in a simulation. These policy gradient methods work by probabilistic sampling of trajectories and don't require us to make those assumptions about the state space that we had to do in order to do Q-learning. My recommendations for future students who would pursue this project is make sure you compute a moving average reward data. It's the most effective way of actually seeing how well these policies are performing. These models are performing at finding a policy, and make sure to sample, because it is very stochastic and very random from iteration to iteration. This needs to be done a bunch of times to really see what the overall behavior is. And make sure to loop through those parameters for optimization, because there are a lot of parameters that change the behavior of this. And I would like to thank the 440 team for a great semester. Thank you, Dr. Fuge, for all of the help you gave me in this course.